Okay, so I know that the double pendulum code is acting strangely. I don't know for sure whether it's behaving badly, but it just seems like, I don't know, it seems like this ought to be swinging to the left some. Yeah, like, alright, so the first thing let's do, I guess the first thing let's do is let's double check, make sure the differential equation matches this guy's derivation. And then I guess I really need to check that the derivation's correct. Alright, partials, substituting, 2 dependent. There we go. Okay. So I've got a negative M2L2. Oh, wait, sorry. There we go. Negative M2L1. Because this is all supposed to be over this, right? Yeah, it has to be because this needs an L to cancel it out. Because this has to have units of 1 over time squared, and there's 1 over time squared. So we've got a negative mass 2 length 1 theta dot 1 squared, negative mass 2 length 1 theta dot 1 squared, sine theta 1 minus theta 2. Excuse me. Thank you. I don't know why I said thank you. I assume you said bless you. Cosine 1, 2 is cosine theta 1 minus theta 2. Plus grav mass 2 sine 2 cosine 12. Grav mass 2 sine 2 cosine 12. Negative M2 L2 theta dot 2 squared. Negative M2 L2 theta dot 2 squared. Sine 1, 2 sine 1, 2. Minus M tot G sine 1. Minus M tot G sine 1. And then it all needs to be divided by L1 M tot. L1 M tot minus M2 L1 cos 12 squared. M2 L1 cos 12 squared. Okay, so the differential equation for theta 1 double dot is set up correctly. Here I've got an M2 L2 theta dot 2 squared sine 12 cosine 12. M2 L2 theta dot 2 squared sine 12 cosine 12. Plus grav sine 1 cosine 12 M dot. Plus grav M tot sine 1 cosine 12. Plus L1 M tot. Plus L1 M tot. Theta dot 1 squared sine 12. Theta dot 1 squared sine 12. Minus grav sine 2 M tot. Minus grav sine 2 M tot. Alright? And all of that needs to be divided by L2 M tot. L2 M tot minus M2 L2. M2 L2 cosine 12 squared. Okay. Have that correct. Yeah, if I remember correctly, this is supposed to be more like a rectangle. So I think I've done this before. So my run, that's all fine. I've got them coming out at the same angle. Let's maybe double check the Euler-Kromer method. So theta double dot equals second derivatives, theta 1, theta 2, theta 1, theta 1 dot, theta 2, theta 2 dot. And I have that here as theta 1 dot, theta 2 dot. 1 dot, 2 dot. Yep. And I am storing theta 1, theta 2, second derivative. Okay. So theta 1 dot needs to get the first one, the 0th one. Yes. Theta 1 equals theta 1 plus theta 1 dot times dt. Theta 2 dot equals theta 2 dot plus theta double dot 1 times dt, and then theta 2 equals theta 2 plus theta 2 dot times dt. Okay. Align the equal sign. That'll fix the problem, but you know, can't hurt. Bob 1 dot pos equals length 1 sine theta 1 negative length 1 cosine theta 1. Right, that's not going to change. I mean that needs to be the same as it was for the single pendulum. Is what I mean. Rod 1 dot axis equals Bob 1 dot position. Okay. Bob 2 dot position is equal to Bob 1 dot pos. So it needs to go out wherever Bob 1 dot pos is, and then go out length 2 sine theta 2 negative length 2 cosine theta 2. So this piece is the same as this piece with the ones replaced by 2's. Rod 2 needs to begin at bob1.pause, rod 2.axis. Okay. All right, so the next thing I know to check is the total energy. So let's do that this way. Oh gosh, what's going to be the easiest way to do that? Let's see. Technically, to calculate the energy, I mean, this is a lovely phase space graph, and maybe it is supposed to behave that way. I don't know. You know what? No, I should check the total energy anyway. Yeah. So technically, to check the total energy, does this guy do the? Oh, wait, he does the kinetic and potential energies up here. So technically I need to put in all of this to calculate the kinetic energy. I wonder if... No, that's probably the easiest way to do it. Okay. So let's do energy equals negative mass 1 times grav, L1 cosine theta 1, length 1, cosine theta 1. I'm not going to bother calculating cos 1 and cos 12, etc. For this part. Minus... Although actually, I suppose... Yeah, no, actually, that would be easier to write. Because I can calculate that here. Because I have all of that here. I'll just return an energy argument. Energy equals negative mass 1 times grav times length 1 times cos 1. I've already got all that stuff calculated and stored. Minus m2 grav. 2 minus mass 2 times grav times... Oh, I need to do my split window again, or it's going to drive one or both of us nuts. One or both of us meaning me or you. Not one or both of us. Although the silent half of my brain could be going crazy, and I would never know. Times cos 1 plus length 2 times cos 2. Alright, so I've got negative mass 2 gravity times length 1. Let me scroll up for y'all. Length 1 cosine 1 plus length 2 cosine 2. Okay. And then I need to add to that the kinetic energy, which is a bit lengthier. So we'll have a half times mass 1 times theta dot 1 squared, right? 1/2 mass 1 theta dot 1 squared times length 1 squared plus, I guess I haven't been putting spaces in, plus, I should though, half, oops, numlock. I don't know how it is I forget to turn on numlock every time I unlock my computer. Maybe it's because I haven't had to do that for the last umpteen iterations of Windows. 1/2 mass 2 times theta dot 1 squared times length 1 squared plus the same thing with 2's. So let's copy and paste, change all the 1's to 2's, or all the 1 labels to 2's. Plus, then we got the cross term. 2 times length 1 times length 2 times theta dot 1 times theta dot 2. I'm rearranging it in a sense that makes sense to me, in an order that makes sense to me. Times cosine 1, 2. Close up that parentheses. Alright, so I've got a plus 2 length 1, length 2. Oh, there's a typo. That should be, if I'm not mistaken, a theta dot 2. That might be the source of the problem below. Right, because if you take, because the whole idea is to take x1 dot squared plus y1 dot squared, and these are the dots over here. So your x1 dot squared and your y1 dot squared is what gives you this thing, right? And your x1 dot squared plus y1 dot squared is going to give you L1 squared. Cosine squared plus sine squared gives you 1. Theta dot 1 squared. So these two added together give you this. This thing squared and this thing squared is going to give you, let's see, this thing squared is going to give you L1 cosine squared theta dot 1 squared, but then that's going to combine with this thing squared to give you this piece, right? And then this thing is going to combine, these two squared are going to combine to give you that. And then the cross terms are going to give you L1, L2, cosine theta 1, sine theta 2, theta dot 1, theta dot 2, L1, L2, sine theta 1, cosine theta 2, and that's where they get the cosine of the difference. Theta 2 dot theta 1 dot, but they need to have both of those. So there's a typo there. I should have derived it myself. That's what I'll probably spend this afternoon doing. Okay, so there's the total energy. M1, 1/2 M1, theta dot 1 squared, length 1 squared plus 1/2. Mass 2, theta dot 1 squared, length 1 squared plus theta dot 2 squared, length 2 squared. And we just confirmed that this one's correct. Okay, so here's what we're going to do is instead of graphing theta, we're going to graph theta dot dot of 2, because that's now being returned as the energy to us. Oops. Theta dot 1. Theta dot 1. Oh, it must be, I call it theta 1 dot, excuse me. All right, so let's do a replace theta dot 1 with, all right, there we go. Theta dot 1, replace that with theta 1 dot. Replace all. Thank you. And now do the same thing, but with the 2's. There we go. All right, F5. Okay, this energy is not being conserved. In fact, it's varying, because if the Euler-Kromer method were messing up, I would expect the energy to tend toward 0, I think, or to tend toward a minimum. But this is actually oscillating very regularly. Okay. So there must be a mistake somewhere in the differential equation itself. So I guess what I need to do is go and solve it myself, or try to find another reference. Let me try to find another reference first to see if we can trace the issue there. So sorry, Josh Altick, found a mistake somewhere. Let's see here. Newton's equations, constraints, blah, blah, blah. Oh, this one comes to us from Gabriela Gonzalez at, looks like, LSU. All right. Oh, goodness. She's going into all the forces and everything. Double pendulum. Yes, please. Please tell me you're not going to do this with Newton's second law. Oh, goodness, you are. Wow. Oh, well, doesn't that make it easier? This is a double pendulum? Are we sure? And the double pendulum, is this doing the same thing? Yeah, this is the same thing that I mean by double pendulum. Because that theta 1 double dot is a whole lot simpler than what I have. All right, let's take a look at where she got that from. We then have 4 differential equations, 4 unknowns. Trigonometric identities can be used. So she's actually eliminated the theta 1 dot. She's actually eliminated the theta 1 dot from here. That seems a bit odd, I feel like. Oh, because she leaves the tension in. Okay, that's why. Okay, yeah. The theta dots are in these tensions. So we don't have derivatives of the T1, T2, but the Cassidy's equation for analytical and numerical. Solution is to obtain two differential equations for theta 1, theta 2 without T1, T2 terms, which is the advantage, honestly, of Lagrange's equations because you just eliminate the tension to begin with. But, to each their own. Let's see here. Okay, so she gets these. Here's Lagrange's equations. Wonderful. Okay, yeah, so she ends up with this, which I guess she needs to separate later. Double pendulum. Here we go. So here's Lagrange's equation. See, you can tell she's from a physics department, phys up here, because she's just calling them Lagrange's equations, not the Euler-Lagrange equations. Which are, of course, the same ones we got. Okay, except you didn't have to go through the tension. Okay, so she ends up with this. So I'm going to have to do a little bit of algebra. I'm sitting here worrying about this. It's linear in theta 1 double dot and theta 2 double dot. It's straightforward to solve. All right, so here's what we're going to do. We're going to call this chunk in front of theta 1 double dot A. So I've got A, theta 1 double dot. We're going to call this chunk B plus B, theta 2 double dot. And that's all equal to this chunk right here, C. And then here, I'm going to do something a little bit different. I'm going to divide everybody by, say, L1 by L2. So I'll have theta double dot 2 plus, and then we'll call L1 over L2D. Theta double dot 1 equals, and then we'll call this whole thing E. Okay, so it gets rid of some of the scariness of it, some of the complexity. So we've got theta double dot 2 is going to equal E minus D theta double dot 1. And so then up here, I just say I've got A theta double dot 1 plus BE minus BD theta double dot 1 equals C. And my handwriting is lovely, isn't it? How do I extend the range of this board? Resize, perfect. Height, no, that's fine. There we go. Okay, cool. So that means I've got A minus BD all multiplying theta double dot 1, and that's going to equal C minus BE. Right, so I've got A minus BD over there, C minus BE over there, because the BE is going to be positive, or it's going to be positive on the left-hand side. And so theta double dot 1, oh, did my Wolfram finish? I just saw my icons blink. Nope, okay. So theta double dot 1 is going to be C minus BE divided by A minus BD, parentheses. Okay, there we go. So that's how we're going to build this thing. All right, I'm going to comment these out because they are handy. Just in case I need them again. All right, so let's start with theta 1 dot dot is going to equal C minus BE divided by A minus BD. And now I just have to, and then I need theta double dot 2, theta 2 dot dot, because that's just E minus D, the other thing. theta 1 dot dot. Okay, cool. So now I need to tell it what A, B, C, D, and E are. Okay, so A is the thing that's multiplying theta 1 double dot. Okay, so A is m tot L1 times length 1. Cool. B is going to be this chunk, m2 L2. B equals mass 2, length 2 times, that is cosine 12. Cool. And then over here, I've got C. So C is going to be m2 times length 2 times, there we go, make it a little visually easier. There we go. Mass 2, length 2. Come on, scroll bar, don't fail me now. There we go. Mass 2, length 2, theta 2 dot squared times sine 1, 2. Now that's getting flipped, so I need a negative over here. Minus m tot times grav times sine 1. D is whatever is multiplying theta 1 double dot divided by L2. So D is going to be length 1 divided by length 2 times cosine 1, 2. And then E is going to be everything on this side divided by L2. So it'll be length 1, because there's a sine theta 2 minus theta 1, so I need to flip that, times theta 1 dot squared times sine 1, 2. That is grab times sine 2. And all that needs to be divided by length 2. There's A, B, C, D, and E, right? So A is m tot length 1, B is m2 L2 cosine 12, C is negative m2 L2 theta dot 2 squared sine 1, 2, minus sign, minus m tot grav sine 1. Here we got a length 1, theta double, length 1, ignoring that part, cosine theta 2 minus theta 1, divided by length 2. Here we got length 1, theta 1 dot squared, sine 1, 2, change the SIGN, minus grav sine 2, all divided by length 2. Okay, so theta 1 double dot is, scroll down, theta 1 double dot is C minus BE divided by A minus BD, and then theta 2 double dot is E minus D theta 1 double dot. Okay. There we go. All right, Python, tell me where my compiler errors are. Ooh, I didn't get any compiler errors. I like that energy function. That is a nice energy function. Okay, so it did not find where the typo was, but I did fix it. I wonder if it is related to that typo, that theta 1 dot. That was supposed to be a theta 2 dot earlier. Uh-oh, I hope I didn't just wreck some guy's thesis. Cool. So this is what we'd expect a double pendulum to look like. That's looking more like what I would expect it to, because you know the like you just saw there, the second bob goes out farther than the first bob and kind of drags behind it. And this this phase space plot is more of what I would imagine it to be. It's a little bit more regular. It's going to end up fitting inside this little parallelogram there. And of course our energy graph is constant, which is exactly what we wanted to see. So we have fixed the problem, and so in the next episode we will take a look at playing around with the initial conditions, the masses of the bobs, the gravitational force, etc., and we'll have a lot of fun with our double pendulum, looking at the behavior that we get as a result. So thank you so much for watching. I will see you next time. Bye-bye.